All right, great. Yeah, so this is communication at any size. So, ooh, do I have slides? I hope everyone had a good lunch. Oh, great, thank you. So, I'm James. You might know me from a couple different places, depending on how much Rust you do. So you might know me from the Rust Embedded Working Group. I'm also serving on the Rust Leadership Council. And I have my company, One Variable GmbH, in Berlin, Germany, where I help big and small companies with mostly embedded Rust, but generally anything that they need help with Rust. So this talk is specifically about a library that I'm working on right now called Ergot, which is a messaging and communication library for Rust. But it's also a little bit about how I think about embedded systems and the kind of way that I want embedded systems to work, even if that's not exactly how they work these days. So Ergot is a library in Rust, but it's very new and experimental. I've been having a lot of fun working on it, but as a bit of a disclaimer, I'm not suggesting you go and start using this for all of your production projects right now. But I am very, very excited about it, and it's something that I've been building towards for quite a few years now. So my personal specialty is usually helping computers talk to computers, and sometimes those are very big server computers, and sometimes they're very tiny computers, like the ones that are in your smartwatch or inside of your phone even. But I sort of have a big problem, and I kind of want to share it with you today. And my problem is, even though I like helping computers talk to computers, I don't really like how a lot of embedded systems talk to each other these days. I've definitely worked on some projects where everything was working well, but I help a lot of people make things start working well because, you know, it's a little tied up sometimes. So sometimes this means internally in the device, when you have different threads or tasks in your embedded system and they're sending data to each other or they're sharing data with each other. Sometimes I don't like the current ways of doing things. So in the past, when we used C and C++ for embedded systems, or the current day for a lot of people, a lot of times this means unsafe everything. You're just kind of sharing data and hope that it goes well, or you have interrupts and your application code, and you hope that you don't step on each other's feet. And this is a scary way to write code. But even today in Rust, where we have a lot more data structures, things like channels, channels can be great because you say, hey, I have these different tasks and I want them to talk to each other. So I'm going to send a message from here to here and here to here and then here to here. And you end up with something that I call channel spaghetti, where all of these are kind of tangled up in knots and things like that. And it works, but it's a little hard to follow sometimes. And then the opposite, you can do something more structured concurrency, especially when we have async, where you put things in mutexes and you share them. And I think that's probably one of the best ways of doing things today, but it still requires a lot of work to get right, because you go, okay, I'm going to split up my things, but then how do I avoid deadlock because I'm trying to grab two things at the same time, or putting them all in one mutex and then one piece of software blocks all of the other software from working. So you can do things right, don't get me wrong, but I don't always love that this requires a lot of work to get this right, and even then, it's not perfect. So that's not just limited to inside of the machine too. Embedded systems are almost always connected to something else. Sensors, other microcontrollers that are doing a different job, to a computer or your mobile phone where they need to, tell that mobile phone what they're reading or what kind of data that they're working with. And it always seems to go one of two ways in embedded systems, I've found. You either go really, really simple. You say, this is an embedded system, it has to be very simple, and you make it a little too simple sometimes. So when we work with sensors over like I2C or SPI, they have a very simple register interface where you say, basically, configuration 23, set value 50, which might, set your accelerometer sample rate or something like that. And it works really well for very, very simple things, but as soon as you want to do something more complicated, it gets a little rough to use. Similarly with things like Modbus, when we have protocols that help you talk to many devices at the same time, they still have this very simple register-like interface where it's just numbers at an address, basically. It's a very raw way of programming and communicating. And then if you've ever used a Wi-Fi modem or a cellular modem, like an LTE modem, you've heard of AT commands before, where even though this was a protocol that came up years ago, it's using text to talk to your modem, like you're back in the 80s. And so we're asking these tiny little computers, these microcontrollers that run in your watch, to speak text to another radio and things like that. And again, it's kind of simple, it works, but what happens if you have to change the settings while you're streaming data? Then you have text that's coming in from all these places, you have to multiplex it, and we're still parsing text on a microcontroller, which is a very silly thing to do. Or when we're talking to a human, we just use a serial console, like you're plugged onto a command line interface. So again, we're asking our very tiny little microcontrollers to pretend that they're a command line application so they can talk to a human. Again, all of this works. I just don't love it. It doesn't bring joy. And the other side of that is going all the way maximum. We say we want to have a protocol that does everything, and it's going to interoperate with everyone. And so we get everything together, and we make these tiny little microcontrollers speak TCP/IP over Ethernet or Wi-Fi. They have whole networking stacks, and you can do this today in Rust. There's some really good libraries for it, but if you just need something that's a little bit more complicated than the first thing, this is pulling in a lot of code just to do something medium difficult. And we have what I call consortium standards. These are like Bluetooth or Zigbee or Thread or things like that. They work really well, but a lot of companies have spent a lot of engineers working on this, and so you have to pay a lot of money to get some PDFs that are thousands of pages long just so you can figure out how to send some messages between devices. And obviously they work. We use Bluetooth for a lot of things, but it's a way on the other side if you just need something a little bit more complicated than what we had before. And even things that are supposed to be for, smaller machines like MQTT, by the time that you have TCP/IP and TLS and MQTT and you're parsing JSON, this is a lot for doing just a little bit more than setting configuration values. And, sometimes the vendors just say, well, we're not going to give you the source code. Here's just a binary library and figure out how to glue it into your microcontroller. Or here's a library. It's 100,000 lines of code. Good luck if you ever have to debug any of that. So I've been complaining so far. It's not that I don't like anyone's code. It's that I think people outside of embedded systems have, in a lot of cases, figured out nice ways to do communication from machine to machine. And in many cases, this isn't new research. This is things that are decades old, and we're not inventing anything particularly new here. So back in the 80s and the 90s, Apple was coming out with their computers. So around 1990, if you went to buy a computer, it would cost you $1,000, maybe $2,000 or something like that. But this is back in the day where networking wasn't what every computer did. So if you were setting up an office with 5 computers and a printer, if you wanted to buy network cards and networking for those computers, it might cost as much as the whole computers just to get networking cards. And so Apple said, hey, how can we make one that's not quite as nice, but like way cheaper, so that if it's just enough that those 5 computers can share a printer with each other, because printers were really expensive back then too. And they came up with Apple Talk, which is like a really weird version of networking. It kind of rhymes with networking, but it's built in a way that these simple computers back in the day could do it, and they could do it with really cheap hardware. And the thing about computers in 1990 is they're about as powerful as the processors that are in your smartwatch right now, if not less powerful. So if they were doing networking and communication in 1990 on those computers, we can probably do that on our microcontrollers too. And then in kind of the more telecommunications era, there's a programming language called Erlang, which is used for building kind of interchange boxes for telecommunication. It's highly reliable systems, and the way that it generally works is you have very lightweight tasks that are sending messages to each other. And lightweight tasks sounds a lot like async await in Rust right now, and sending messages to each other sounds a lot like how we do things in Rust a lot of times. So this is an era of computing where they went, well, yeah, we're just going to make something that's very lightweight and we're going to send messages to each other. And they were able to build very reliable systems for telecommunications in. And then kind of in the 2010s, there was another group of developers who went, I'm tired of how complicated and heavyweight everything is, and we want to do high performance, low latency communication, I think primarily for the financial markets and things like that. And they went, well, we're going to come up with a protocol and call it 0MQ. It came out of some other work. There was an earlier thing called AMQP. They thought it got too complicated, so they made like a littler version that they liked. And I really like their approach to a lot of this messaging because they say instead of having a protocol and a spec for everything, we're just going to give you a couple building blocks that work together really well, and you decide how to glue them together for your application, which is an approach I really like. And then people have been building reliable back-end systems for servers and websites and apps for years and decades now, and they've got approaches for discoverability and scaling horizontally, and they've kind of already solved a lot of these challenges, and I think we should take some of their notes. So, like I said, I like parts of a lot of these ecosystems, and particularly how they help computers talk to other computers. So we should just go and borrow those good ideas. Instead of, pretending that embedded systems can't learn anything because they're so different, we can borrow some of those good ideas. So this is where Ergot comes in. Ergot is the library that I've been working on that does messaging in Rust, and it borrows a lot of the ideas that I've been talking about so far. So Ergot as a library is kind of based around this thing called a net stack. So when we're thinking about the code, this is kind of the core of how the library works. And the interesting thing about the net stack is it's not some runtime, it's not some library or anything like that. It's a really simple data structure. And its job is you give it messages, and its job is to figure out where those messages go. So put messages in, and the messages end up where you want them to go. So if you're building an application, you add some sockets. You say, hey, these are destinations for messages to go. So when you put a message into the net stack, it figures out which one of these sockets it comes out of. So you can spin up async tasks and say, hey, my task is going to have a socket, which means people can send it messages. It's like having a mailbox, basically. And then when we want to start talking to other computers and other systems, I have this thing called a profile. And the profile's job is to handle any message that goes somewhere else. And the reason that I call it a profile is because different kinds of devices need to handle routing differently. If you're a very simple device, you might just have a simple way of saying, well, that message goes over there. But if you're a more complicated machine like a PC, you might need to do a lot more work to figure out where those messages go. So if you start building up a network of devices like this, let's say over on the end we've got this little microcontroller that's just on the end of the chain, and it's using a serial port to talk to some other microcontroller. Routing is really easy there because there's only two choices. Is this message for me, or is this message for not me? Because if it's for not me, it goes out there. And if it's for me, then it goes into one of my sockets. And when we've got our slightly bigger microcontroller, maybe an ESP32 or an RP2040, it gets to work a little harder. You can see the profile's a little bigger because it has to choose this way, or for me. And then on our big, powerful device, our mobile phone, our PC, a server, we have to maybe figure out a lot of different choices here, so it can be more powerful. But by making this bottom part the same on all these machines, but the profile be the thing that kind of scales, you can end up with a very, very small piece of code that does just enough networking where this device can play nice with a much larger device for a very low cost. So, like I said, I've already started borrowing some of those good ideas that I mentioned earlier. So, sockets are nice because I feel like most people understand what a socket is when I say it. You go, okay, it's kind of like where I'm going to receive data from, and I have to open it. And so I have to open the socket, and once it's open, it can receive messages, and then when I close it, it'll stop receiving messages, and if a socket is closed, I can't send messages there. So I think it's a good way of thinking that I think a lot of people are going to be familiar with. So this is a little bit of Rust code. Don't worry about understanding all of it, but the big part is we go to our net stack, and we open up a socket, and then we attach it to the net stack by subscribing to new messages. And then we can just write a little bit of async code where we go wait for a message to be received. And so we can await in async, and then anytime we receive a message, it will get notified, and our async task will await, or will wake back up, and then we can print out the message that we just got. Now, one thing that I've also been very opinionated about in this project is that I think all of my sockets should be type safe. So instead of TCP/IP, where you just get a bag of bytes or a stream of bytes, so UDP you just get a frame, or TCP you just get bytes, I say no, you should get Rust data types out of this. You will open up your socket and say, I want this struct or this enum and things like that. So when you open up a new socket that's a server and you attach it to the net stack, you can start serving requests, and this request takes a floating point and it gives back a U64, an integer. And we can see that it takes that floating point, writes it to the PWM to set the LED brightness or the motor speed or whatever it is, and then we give back what time we did that. And that way, we never have to think about serialization and deserialization. It's Rust data in, it's Rust data out, which means there's not so many places to go wrong with the programming. Now, addressing, so the addresses we give to our devices, how we do routing, how we handle different interfaces. I borrowed a lot of this from AppleTalk because, like I said, AppleTalk was figuring out how to get cheap networking on cheap devices and how to make it work. So they made a lot of things modular and lightweight in a way that I like. So I'm borrowing research from the early 1990s to figure out how we should get our tiny microcontrollers to talk today. So when you have a network like this, you might have a PC over USB to a Raspberry Pi 2040, and a bunch of even smaller microcontrollers over here over RS-485. And so this is a network. We've got one network segment on USB and one network segment on RS-485. And so addresses in Ergot are a 16-bit network segment, an 8-bit node ID, and then an 8-bit port for our sockets. So we can see that the PC on this interface is address 1.1, and then this is 1.2, and we can see that this is network segment 2 with 4 devices on it. And the same way that you use IP addresses, you can find those addresses, and then you can send messages to those addresses. And again, from Erlang, I really like that idea of message passing. We set up little state machines that receive messages and send messages. So you can listen to 2 sockets at the same time, and then wherever a message comes from, you can handle whatever that message is and then either send a message back or don't. And it makes a really easy way of writing these tiny little async state machines that do one thing at a time, which makes reviewing the code really easy and understanding what that code is supposed to do usually fairly straightforward. You just go, okay, message in, change my state, send a message out, and it works really well. And then from back-end systems, things like observability or discoverability. So we can use the log crate in Rust, the same log crate you might use for servers. We can use them with Ergot, and Ergot will actually be a sink for the log crate. So you can just send log messages on your machine, microcontroller or desktop, and they'll get given to the network stack, which will send them out over the network. So you can collect them into a log collector, like Honeycomb or any of the other services that are out there, and send your logs off of your machine. And this works either on the desktop with the standard library or alloc, or even on a microcontroller. This is one of our ESP32 examples, where we can actually use the serial port and send all of our logs over the serial port like a network interface, basically. So this works both on desktop and tiny embedded systems. And for discoverability, if you want to find another device, why don't you just ask the network? So we have built-in ways of making requests to the network where we can say, hey, I'm looking for a socket that can do this. Does anyone have one of those? And we can send it out to the network and see if anyone says, yes, I have one of those, come talk to me. And they'll give you back their address, and then you can start communicating with them. So we don't have to hard code everything in our embedded systems. It's like DHCP on your desktop. It just auto-configures and it works. So why now? Why hasn't this been possible in the past, and why is it something that we can do now? Well, I like to use the analogy with Rust, in that Rust had the benefit of starting 25 years later. And when you start later, you can just take everyone's good notes and start from there instead of making a lot of mistakes along the way. And so we can do the same with Ergot. We can say, what's the best way of communicating these days, or even in the past in some cases? And instead of starting from scratch, we can just go, let's take some ideas that we know work pretty well or can be combined to work pretty well. Because when you're building embedded systems, I want to be able to turn your circuit board that might have a bunch of microcontrollers on it. You might have one microcontroller to be a motor controller, and one to read sensors, and one to control LEDs and displays and things like that. And instead of making them all their own standalone system, why don't we make them just a local area network that works together? Because this is what a local area network looks like, and if all of these can be running Rust, and all of them are able to open up network sockets and things like that, you can build your embedded systems the same way that you build distributed systems on any other sort of platform. And I find this is a very pleasant way to build embedded systems. So if this seems exciting to you, then Ergot definitely needs your help. We have quite a few people hanging out in chat, but I can always, I would love to have people ask questions, figure out where my docs are not so great for Ergot right now. To try out, we have a bunch of demos for a bunch of different platforms, Raspberry Pi, ESP32, ones that you can just run on your desktop as well. So give them a try, and if you have a platform that you want to use Ergot for, let me know, and we'll make a demo for that platform too. And then give me feedback, and if there's anything that you can do to contribute, that would be amazing. So Ergot is open to any good ideas, new or old. So if you want to come join, we're on GitHub, so github.com, James Munn's Ergot. All of the code examples, the docs are on docs.rs, and we have a matrix chat where there's quite a few folks, some folks even in the audience who are in there hanging out and trying out Ergot already. So thank you. This is Communication at Any Size, and I'm James Munns.